Let me ask who has questions? Ed, it looks like Ed Becknell. Ed, sir, do you have a question?
No, I don't have a question. I was just pasting a link with Ning Lee. It had been shared on WhatsApp earlier this week. So I just wanted to share with the group.
Okay. Okay. Well, thank you. Okay. Well, let me see. Who else has a question for Tony? Jeremiah. Go ahead, sir.
Definitely. So you've worked with gravitational interactions and superconductors, yeah?
Yes. Mm-hmm.
So I have to, of course, ask you, take this fine opportunity to ask you about Podkunov and POR. Mainly, it's POR that I'm interested in, because what they're claiming now is that they no longer need superconductors. They now can use some room temperature materials that don't require incredible amounts of cooling. In fact, they even say they can operate in air. And these room temperature semi-superconductors, there are some materials that act like superconductors that are, I guess, according to them, graphite based. They're claiming impulse forces, gravitational impulse forces being generated by those systems. And I was wondering what your opinion was on the mechanism of action that's producing that radiation that's emitted out of one side.
That's what I was talking with Tim earlier about. It's the new work that Prokletnov's doing. I don't know much about that, but graphene is basically a room temperature superconductor. So I could see some effects coming from graphene if that's in there. But I was thinking he was talking about it being some kind of material that had some kind of ion something or other in it. But like I said, I don't really know much about what he's currently doing. If anybody has anything, please email it to me. I'd like to review it.
I can certainly send you POR stuff. POR has released several papers, and there's another more recent one that I just read. It's actually better than all the previous ones. And so what they have is some kind of arrangement where they take some dielectric materials, they take some graphene, and some other kind of, I think, a metal. They sandwich all this stuff together and press it into this disc. And I'm guessing that, and I try to model it in my head, how the electron flow through this system might actually yield some kind of an impulse force under a high power impulse. And so
well, my model will tell you how the electrons do that.
Yeah, I'd love to hear that. I'd love to hear that from you. That's what I'd really like to hear.
It's kind of in my paper, but basically when I say object, I mean something with mass. All objects carry this energy shell around them. So even within matter itself, you have matter that has this energy shell around it. So if you move the matter inside matter that has an energy shell, that energy shell pushes out in the direction on the shell around that total matter outward. And when you push this outward, you're changing that thin shell or the wavelength of the quantum energy in that shell. And if the one side gets large, the shell gets larger than the other side, then you move in the direction that you're pushing this out. And that's maybe what they're doing in there. But you have to if you don't vibrate it, then you just get an impulse and you stop. So you have to pulse it, let it relax, pulse it, let it relax. And if you pulse it at the right frequency, you can keep this shell outward and keep yourself moving.
Oh, interesting. So you're saying it's possible to actually generate a continuous force with an RF signal, perhaps, with the right material.
If you're operating on a mass, there is some evidence. In fact, there was another guy that presented at Tom's Coffee, Dr. Rancourt, who claims to have put a laser between a mass and a mirror, and the mass actually moved towards the laser beam. So the laser being energy with a wavelength, he's changing this shell around that mass and causing it to, in other words, if he's putting energy into that shell, the shell's growing and the mass is moving towards the increased shell.
May I ask for clarification? You're talking about the experiment where basically there's this mass, it's on a torsion balance, it's hanging freely, and then he puts a high power laser beam right next to the mass, right? And then it's pulled in effectively to the beam? Is that what you're talking about?
The beam's between the mass, I think, and the mirror that he had there. And yeah, it's being pulled towards the beam.
Yeah, that's I'm familiar with that experiment, and it's very, very interesting. I know somebody else who's attempting to replicate it with a huge amount of LED power pumped down a reflector tube, you know, the type that you might see inside of a bathroom in a one-story house that would take the sunlight and bring it into the house. So he's trying to bounce a bunch of light back and forth and try to measure a pole or a gravitational field towards said light-filled tube, just to see if that light has mass and if it has an effect. So I think it's an interesting experiment on those same vein. But I do have a question for you about electron acceleration, something that I've been dying to know, and I think your model probably answers it. If you have an electron that's emitted from a cathode, and it starts out basically at rest, and it's accelerated the entire time towards the anode, and by the time it reaches the anode, effectively, it has accelerated, therefore it's changed continuously into its own inertial frame of reference, no longer bound to the inertial frame of reference of the cathode that emitted it. And because it's continuously growing farther and farther away from the cathode, its consequent increase in velocity and increase in relativistically amplified electric field is weaker as far as the cathode sees it than when the anode will see it ultimately when it impacts the anode and its momentum is suddenly discharged and returned to the anode as a forward force. My question for you is, would the system be equal and opposite in terms of total forces in that system, or wouldn't the relativistic amplification of the accelerated electron yield a force towards the positive electrode?
But basically, when the electron is accelerated, then there's an opposite force in the opposite direction. But typically, that's balanced out by when it hits the negative end on the other side. So those two forces tend to balance out, and your system would sit there and jiggle. But my model says that the acceleration itself of those electrons actually induce an acceleration on your total system, which would be your whole cathode system. Which somebody was mentioned that something about some cathode where they were seeing the force, what Townsend Brown was seeing a force.
Yeah, his Coolidge tube, that's how he started with it. And I actually ordered a Coolidge tube on eBay a couple of days ago that arrived broken, unfortunately, but that's okay. We'll try again, just to recreate his original experiment. And it was one of the old school ones, and I noticed it's very interesting. The cathode on the Coolidge tube, I have it sitting here too. Great. So this is from a 1926 Westinghouse deep therapy X-ray machine, and this cathode is tiny. The anode plate is roughly about this large in comparison to the cathode. So the asymmetry here is tremendous, and there would be a divergent field coming off this thing as it emits electrons. Inside there, you can see a tiny little coil. So this piece of equipment is different from modern X-ray equipment in that the cathode was much smaller than the anode, and this is the kind that T.T. Brown would have had in the time that he was working with this stuff. It would have been an asymmetrical capacitor like this. But the electrons either way would have been accelerated off that cathode, and he said that he noticed a force towards the positive electrode, which means that the anode would have been, forced along. So are you saying that the field produced by the acceleration of the electrons acts on the body in the direction of the acceleration or in the opposite direction?
According to my model, the acceleration should be in the same direction as accelerated electrons. The problem we run into is that since the shells around these electrons are carrying momentum, when you hit that plate, the momentum keeps going, just like the impulse experiment that Bukletnov did. It leaves your system, and if it leaves your system fast enough, you don't get this force that I'm talking about. It's kind of left your system.
But so you could effectively have something in front of it that could receive that force. Yeah?
Yeah. There's an experiment I want to do, which I can't talk about, so I'm not going to tell you what I do.
Yeah, Tony, what you're describing, it sounds like, and what Jeremiah is jumping into is basically the force beam experiment, right? Where the momentum continues on beyond the experiment. And I mean, potentially.
It sounds like Ben just gave us a recipe on how we might want to pursue something like that.
Well, guys, before we continue with questions for Tony, I should mention that Paul LaViolette mentioned a fellow named Frank, who was a 1950s radar operator. And in fact, let me ask him if he can unmute himself real quick. And we're ahead of time. So Frank, are you with us?
Yes.
Okay. Sir, I want to welcome you. Now, we're actually in the middle of a Q&A session for Tony Robertson, but I noticed that you joined us. Paul LaViolette had said that you were a radar operator during the 1950s with the UFOs over DC incident. Is that something you might be open to discussing today?
It was my father, Frank H. Ferguson, Frank Harvey Ferguson, that was in charge of the 1952 review or observation of both there were two in 1952, DC, here in Washington, DC, UFO sightings. And my father was in charge of the whole monitoring of both events. He was a radar expert at the time, and he was also in charge of all the visual and the planes that went up to intercept, in quotes. And this was my father's introduction to things that he thought just couldn't happen, like the UFOs appearing and then disappearing simultaneously, visually and on radar. He also had all the data database of their movements, which he at the time in 1952 thought was impossible for anyone inside to live at those turns and speeds and so on. But to make a long story short, he worked with J. Archibald Wheeler, and he had young fellows working with him who I knew and talked to in the kitchen in the 50s, who I just knew as Dick. And Dick turns out to be Richard Arnowitz, Dr. Richard Arnowitz, who is the A in ADM, quantum physics. So Dick just worked for my dad, and I used to have conversations with both of them. And in 1970 was the last time I saw my father. I talked to him about his work, and he said to me, "We have been doing interstellar travel for some time now." That's in 1970. So I talked to him for about a half an hour after he told me that, and I asked him a lot of questions. And some of the questions were, well, Dad, I know the nearest star is 4 light years away, and I know that you can only travel at 10% at the speed of light, so it would take 40 years to get there and 40 years back. And he just laughed, and he pointed out that we've been traveling to much further than the nearest star. And then I said, well, at those speeds, Dad, you would run into things. And he just said, no, you go through them.
Well, Frank, if it's okay to pause you on this, I would love to I mean, if you're open to it, it's about, let me see, 2:45 Pacific. I'd like to do a few more minutes with Tony's presentation, make sure everybody gets their questions.
Oh.
But if you're open to speaking about this more.
My question to Tony is that from listening just to the few minutes that I listened to, it seems that he's making the assumption that time is an aspect of gravity. Is that right, Tony?
Well, I didn't address time as an aspect of gravity, but in my papers I've written, I do talk about time dilation within the papers, but that's related to how the aft and forward energy shells react to each other rather than as far as time. I pretty much confirm that the model that I've got for these energy shells and space-time are the same thing. So anything you say about space-time should be true with this model too, because they're the same thing. The only thing difference that this model tells you how you can change these thin shells so that you can work towards a warp drive or at least some kind of space drive system, where space-time tells engineers nothing about how they can design anything.
Right. And one thing that I think my father would say at this point is, well, of course, it's all a matter of Laplace transforms.
Yeah, not a space-time metrics person, so you're losing me on anything. I'm an engineer, and my aspect was to try to find out how we could build a warp drive, and the space-time metrics tells me nothing. Now, basically, the only thing they tell you is that it's not impossible to build one. It just doesn't tell you how to build one.
Right. And another thing, maximum of my father was that 50% of knowing how anything is done is knowing that it has been done. And this is what he was in on. He and people like Arnawood were from Wheeler were in on what had been done. And this was a problem for people like Richard Feidman, who was a good friend of Arnawood's. They drove across country and so on. But Feidman was never allowed to know for sure what had been done and what hadn't been done. But once you know what has been done, you're halfway there to doing it.
Yeah.
Awesome. Okay.
Well, my model basically says that you create warp drive anytime, or create a warp field anytime you accelerate anything. So to get to faster than light, you just need to know how to couple to these fields in a way that can get you to the speed of light. In fact, in my paper, I talk about the fact that my model does permit you to go faster than the speed of light.
Right, and faster than the speed of light is the slowest interstellar travel. There's space-time warpage, but the real way to do it is what they call portal travel. That's where you open the door and you're there.
Yeah.
I think we need to get the warp drive first.
Yeah. Well, yeah. So let me
keep in mind this, what has already been done.
Oops. Okay. So Frank, let me put you on mute, and we will definitely come back to Frank. And again, I owe you guys an apology. I owe you guys an apology for interrupting Tony's discussion time. Let me go to Will Riken. Will, did you have a question for Tony?
No. Yeah, I have a question for Tony.
Sorry.
So you talk a lot about pulsing. So are we looking at like nanosecond pulse, pico, atto, femto? What are we looking at here in your experiments?
Well, I haven't really done any experiments. If you look at Woodward's experiments, he's what frequency was he at? Shoot, I forgot what frequency. Wasn't very fast. It was fast, but not extremely fast. But it probably depends on what species you're accelerating as much as it is the frequency that you're doing it at. If your mass gets large that you're accelerating, the frequency probably goes down. And if these masses are tiny, like say photons or something, your frequencies probably can go up. But you just got to figure out how to interact with the species you want to accelerate with.
Well, you're just talking about repetition in your explanation,
Mhm.
going back and forth. And so all I'm asking you is, what is the repetition rate that you expect that these things work at?
I can't answer that at this time. I just know that you have to have a repetition or you won't, or you go back to a steady state condition and you basically stop unless you're in space and there's nothing
But
stopping
you're
you.
basically saying the faster the repetition rate, the greater the effect.
Greater the acceleration, yeah. Mhm. Now you're gonna have losses because you're gonna have resistive losses that you have to account for and stuff. So, you know, within certain materials, you're gonna heat it up and melt it down if you go too fast. So you're gonna be kind of limited by the material that you're actually causing this repetition in. In fact, my model basically says you have to have a mass that you're operating on, and you operate on the mass, and the mass changes the energy shell around it, which then couples to you the energy, the quantum energies that's outside of that.
Okay, thank you.
Mhm.
Okay, thank you, Will. Let me see who else has questions for Tony. Oh, Michael Boyd does. Michael, sir.
So yeah, I'm curious if basically you're assuming as you get closer to the mass that the let's say the space-time is different. It's so like we assume gravity is linear with distance. Essentially, it's a acceleration. It's a inertialess free fall, that kind of thing. So it's a but if the gravitational field would change as you get closer to the object, would that mean it's not linear anymore?
My model doesn't say that gravity is any different than we know right now. It's the same thing as what we do now. The only difference is if you look at it, that since all matter has its own little energy shell around it, it has its own gravity well around it. And when it falls into another gravity well, it's distorting that gravity well as it moves down in the gravity well. But as far as the gravity, it doesn't change from what we already know.
So you mentioned that on one side you had what you call expanded, and the other side denser space-time of the object moving. Would that work? Would your model work at smaller, real small dimensions? I'm curious.
I think I don't know how small a matter it would work down to, but the guy that I got this information to work into my model, he was talking about photons and electrons. He
photons don't have mass, but electrons do. So,
but he basically proved that their energy shell around the photons and electrons the energy density is equivalent to the mass density, which is what I did in my paper. It showed that the energy density around the Earth is the same as the density of the Earth. So that tells me that it works at least down to photons.
Yeah, well, that's pretty small. That's you know. So
Yeah.
What I got your email, and so what I have is I have a large data set of, I know all the dimensions of my nano bumps and nano pits. I know all the dimensions of distances between the sensor. I know the rotational speed, the radius of the feature, and all that kind of stuff. I'm curious if I could send you all that data, if maybe you could try and stick it in your model and see what kind of results you get. You game?
I don't know if I have the time to do that.
Well, you don't have to do it in a big hurry. You just do it when you're ready.
Yeah, I can't answer that without actually seeing the data, because I saw your presentation 2 weeks ago, but I'm not sure I followed what you were doing. I don't know how these pits and stuff fit into my model. You have
Yeah,
to.
I was going to ask you about that. Obviously a bump would seem to follow fairly straightforwardly with your model, but a pit would be, so you'd have to, well, let's do one at a time and see what we come up with. maybe we find something new.
Oh, you can send it to me. I'll take a look at it, but I can't guarantee anything. That's the
Okay,
point.
that's
You know,
fair
I'm
enough.
I'm retired now, but I have less time now than I did when I was working.
Okay, well, thank you again, Michael. Okay, so let me go and ask for more questions for Tony. And again, I should apologize yet again to everyone. I've kind of interrupted our own schedule here, but let me see. I think Todd was asking, Todd was discussing, oh, there, Mark. Okay, let me go to Mark Sokol. Sir?
Oh, okay, thank you. First of all, great presentation. And you mentioned before that you thought there was a good chance that PodClomp's impulse experiment will work. We actually tried that once already, actually twice, with negative results. What do you think would be the mechanism that makes it work?
I have to understand what you did first, because from what I've seen, most people who have done the Kletnoff experiment did not do it exactly the way he did it. There's just things that, the disc itself was peculiar. Even I don't know, a lot of people don't realize it, but he was using a helium gas, not liquid nitrogen. So he wasn't to liquid helium, but he was temperatures, but he was a lot lower than nitrogen temperatures. And most people can get nitrogen easier and they can't get helium. So that's one data point that you got to concern you is what temperature were you really going down to when you did this. The other thing you got to concern you with is what your vacuum was. He was only down to about 1 torr, which is actually pretty high from vacuum standards. So there were a lot of atoms in there in the chamber, not like the air, but there were still atoms in the chamber. And so if you were going down too low a vacuum, then you wasn't collecting these atoms that were actually being accelerated to cause this effect. It's not something being generated from the superconductor itself. It's these atoms that are collecting on the superconductor that are being accelerated during the discharge that's causing the effect.
We didn't even use a vacuum chamber in this iteration, so that's good information to know. And you're saying, does the type of superconductor matter? Type 1 versus type 2?
I can't answer that 100%. I can just say what he used was the YBCO, but it was 2-layered and it was melt textured. So the superconductor had a lot of Josephson junctions in the superconductor.
That's what I was going to get to. How were those Josephson junctions made?
They form naturally when you melt texture it. Plus the 2-layer, then you have a Josephson junction between the non-superconductor layer and the superconducting layer too, which may play into all this. Because eventually what you're trying to cause, I probably shouldn't say this, is you're trying to cause a Josephson junction between the atoms in your chamber and the superconductor. And I'm not going to tell you why.
Okay. Do you know what material they used to combine the two superconductors together?
Well, what I did was making them was just put the non-superconductor powder in and lightly pressed it, and put the other powder on it and lightly pressed it, and then went and pressed both of them more tightly. But
okay.
How he made the superconductor is really unknown, because from what we heard from him was that he borrowed the superconductor from somebody else, and somebody else made it. Or that was for the larger one. Now, the second one, I don't even know where he even got that one.
Also, we were considering using tin oxide, which is known to be a super insulator at cryogenic temperatures. And it could actually be a semiconductor as well. If you change the magnetic field, it can then allow the electricity to flow. Would that work for the Josephson?
I don't know, but I would love to try different types of superconductors and see if you can form this atom cloud on this atom cloud is what's the important thing.
I should mention that Mark is still digging pieces of the last superconductor out of his shop walls. So
actually, they're in a box over here. I was organizing the lab, and we're getting more superconductors in from Australia. Nice 2-inch size discs that we're going to use for the next iteration of this experiment. But it's good to know that the vacuum level is very important. And also, what voltage was he running it at? Is it more about the voltage or more about the current?
I'm not sure about that. The 512 kilovolts is actually unique. It's actually the voltage where you can annihilate and create electrons. That could be important.
We have that capability here at the lab, 960 kilovolt March generator.
Yeah, that could be important in creating these tiny fluctuations of particles that aren't electrons, you know.
Oh, okay. That's all very interesting information. We'll use that in our next gravity impulse experiment. You're welcome to come join us. It'll probably be in a month from now.
Where are you at?
Hawthorne, New Jersey, North New Jersey.
Yeah, it's a long drive, but I don't know. Let me know. I'd like to see what you're doing with the setup before I would decide to come up there, so I can decide whether I'm wasting my time or not.
Or whether I'm wasting my time.
Okay, well, thank you, Mark. So let me see, who else has questions for Tony? And I think we're just about 2 minutes before the hour. And Tony, you're way ahead of schedule. But if you'd like to wrap things up at 3, then I'm okay with that. It's up to you, sir.
Yeah, like I said, I didn't want to get into the acceleration stuff because there may be some experiments that we're going to do down the road, and I don't want to really talk about that too much. But if you do pull my paper up, a lot of that information is in there. So
okay, well, so let's do this then. I'd like to have everyone thank you again for presenting, and I would love to have you back when you have more to present or other topics or anything like that. I mean, again, I'm pleased as punch that you're willing to join us. So everyone, let's give Tony a giant thank you. Sir, thank you yet again. And I should apologize for disrupting things. We're just a little bit of scheduling change.